Welcome, everyone. Thank you so much for being here. I'm sorry we didn't have a bigger room for you. I wasn't expecting this many. My name is Susanna Kohler. I'm the AAS press officer, and I'm assisted all week by Deputy Press Officer Carrie Hensley up front here and AAS Media Fellow Benjamin Casses. And we have got a fantastic press program for you set up here at the 243rd meeting of the American Astronomical Society. We're so glad you're all here. So before we get started, I just want to ask everyone to make sure that your cell phone is silenced and there won't be any sudden interruptions. Going forward, we're going to have press releases from, I think, everybody at this table, possibly. And all week there will be press releases coming out from the majority of our speakers. So those will be posted as part of the press kit. If you got the media announcements up until now, you got one that was an online version of the schedule. And in that schedule, we're going to start linking out the press releases, the slides from the presenters, any other information you might need as further resources. So we're going to record these press conferences. They're live streaming to YouTube currently. And at the end of the day, we will upload those videos. So those should be available by the next day for reviewing later as well. And those will be archived on YouTube. So you can go back and watch all of yourselves. Everybody's favorite thing, right? So those will all be available. So the way this is going to work is I'm going to go through and I'm going to give a brief introduction right now to the topic, the panelists and their presentation titles. Then they're going to come up and they're going to present one after the other, give their talks. And then at the very end of this, so please hold all questions through that. At the end of all of their presentations, we'll move into a Q&A session. And that's when you can ask all of your burning questions for all of the panelists, and we'll fit in as many as we can in the time we have. When we get to the question session, and we'll try to remind you of this then, but please, if you are asking a question, can you first identify yourself and your affiliation before asking the question? That will help. And then identify who the question is for. This goes also for those of you who are joining us online, which appears to be not too many, so hopefully everything's working. But those of you who are joining online, if you could also put in your questions in the Q&A section of the Zoom webinar and identify yourself and your affiliation when you put in the question, that would be great. Okay, so today's first press conference is titled Dust, Clouds, and Darkness. You'll note that a lot of these press conferences are a bit of a hodgepodge of topics. We had a lot of last-minute schedule changes, so please forgive that. Some flight cancellations caused a few rearrangements, so if you're looking for the most recent version of the schedule, that's online. Please double-check that. And our presenters today, first up will be Natalie Butterfield from NRAO. And she's presenting a polarized dust ring in the Milky Way center, a magnetized dust ring in the Milky Way center. Then we've got NASA telescopes show famous exploded star in its best light. Some great imagery from Dan Milisavljevic from Purdue University. Then we'll be hearing about the mystery of star formation revealed by hearts of molecular clouds from Koda and Amanda Lee. Jin is from Stony Brook University and Amanda is from the University of Massachusetts Amherst. Then Karen O'Neill from Green Bank Observatory will be telling us about the dark galaxy J0613+52. And lastly, Alison Coil will present on the origin of odd radio circles. Alison is here from the University of California, San Diego. So with that, let's see if we can go ahead and get things going with minimal technical difficulties this conference. Natalie, come on up.
Sounds pretty low.
My mic is on, but maybe we can turn it up a bit. Testing, testing. Can you guys hear me in the room? Test. Yes. Oh, more? I'm hearing more. Okay, a little higher. Okay. How are we doing? No feedback yet. Great. Oops, thank you. Save dispatch. We're just going to get out of this. Great. Okay, take it away.
Hi, my name is Natalie Butterfield, and today I'm going to be presenting data that is part of the Fireplace Survey, which is the Far Infrared Polarimetric Large Area CNZ Emission Legacy Survey that was taken with the SOFIA telescope. There are currently 2 publications for the survey that are currently on archive. Fireplace 1, which was accepted for publication last month and presents the first data release for the project, and Fireplace 2, which was just posted on archive on Friday. The QR codes for both of these publications is listed on the slide here. For today's talk, I'm going to be discussing the results from Fireplace 2, which highlights a serendipitous result from the Fireplace survey, namely the detection of a magnetized dust ring in the galactic center. So the center of the Milky Way galaxy is a dynamic environment that contains a large amount of dense gas on the order of about 10 million solar masses that is packed closely together, indicating that interactions and feedback from these different sources is quite common in this region. I've listed several of the prominent clouds in the galactic center, including the supermassive black hole, Sagittarius A star, along with a few other star-forming regions like Sag B2 and Sag C. The dust cloud that I'm going to be presenting on today, the M0.8 minus 0.2 dust ring, which is what I will be focusing on for today's talk. This region of the galaxy is much more extreme than other regions in the Milky Way, with properties that are typically only found in other galactic nuclei and in high redshift galaxies. Measurements of the magnetic fields in this region are much stronger than field measurements in the galactic disk, with field strengths on the order of a few hundred microgauss. The structure of the magnetic fields in this region is also unusual when compared with other regions of the galaxy, containing many non-thermal threads of emission that can be observed in the radio, which is shown here in yellow, the most prominent of which is the radio arc, which I have annotated on this figure. These threads are thought to trace the magnetic field lines, and you can see several of these threads throughout the galactic center. These threads are generally oriented perpendicular to the galactic plane, which is shown as this faint horizontal dashed line across this figure. However, when we look at the infrared and submillimeter, so similar wavelengths to SOFIA and the Fireplace survey, we observe a field that is oriented more parallel to the plane of the galaxy, suggesting that there's this bimodal distribution of magnetic field orientations in this region of the galaxy. Now, the primary method for measuring the magnetic fields at infrared wavelengths is a technique that's called dust polarization, or BRAT theory. So now what BRAT theory is doing is it's the idea that these dust grains in these clouds are spun up by radiation from nearby stars. These dust grains then align with the magnetic fields that are shown in this figure here. And then the radiation from these dust grains in the infrared is polarized and then can be detected with telescopes like SOFIA. And using that polarized data, we can then infer the magnetic field directions. And that's what we're going to be showing in today's talk. So when we make these measurements for the dust ring, what do we see? So here's our cloud again of our image in the galactic center with a box highlighting our source. And so this is the image that we see when we look at the magnetic field lines towards this source. So we see in this figure, which is showing a line integral contour for the SOFIA magnetic fields in the cloud, that the magnetic fields show this curved-like morphology that trace the ring-like structure in our source. Now, another way that we can look at our source is to, in order to better understand the circular nature of the magnetic field, is to overlay a polar plot on our structure. And so this is shown in the figure here on the right, where the magnetic field lines are shown as pseudo-vector lines rather than that continuous contour level that we were showing in the previous image, but these are using the same data sets. It's just illustrated a little bit differently for different purposes. So using this polar coordinate system, we can then measure what the magnetic field strength is as a function of radii. And so that's what's shown here on the figure on the left. And what we found is an increase in the field strength at a radii of about 4 to 5 parsecs, which correlates to the brightest emission in this figure that's shown here on the right. So the red regions were showing really bright emission, and that's where we see a lot of the strongest or the highest magnetic field strengths in this region, and then a steady decrease as we move to higher radii. So this suggests that the magnetic field is being swept up. So as you have your expanding shell sweeping up material and compressing the magnetic fields, resulting in this increase in your field strength across your source. And so the idea that we have an expanding shell is consistent with previous measurements of velocity motions across our source, which suggests that the ring is an expanding shell and most likely a supernova remnant based on the energetics that you need to produce this expansion and the velocities that they observe towards the source. So now how can you sweep up material resulting in stronger field strengths? So here's a very simplistic schematic that's showing the expanding shell in a uniform magnetic field. So in stage 1 here, we have the ambient galactic center field with a point source towards the center. Then you get this explosion or this expansion that starts to sweep up the field lines, start sweeping up the surrounding material, collecting it up. And then in stage 3, where we get this collection of magnetic field lines resulting in the stronger magnetic field strengths that we observe towards the rim of the source. So therefore, the compression of the magnetic fields by the expansion is causing this increase in the field strength that we observe, indicating that we could be seeing a similar phenomena here in this dust ring that we observe towards the galactic center. So now to wrap up my talk, at the end, I would like to end on my title slide with an image showing an LIC for the full fireplace survey. So this is going to be titled Fireplace 3. Fireplace 3 is expected to be submitted to the journal and archived later on this week. If you would like to hear more about the fireplace survey and all of the interesting results that are coming out of this large collaboration, please see Thursday's talk on the Galactic Center at 10 a.m. We will have several talks on dust polarization in this inner region of the galaxy, including Fireplace 3, which will be presented by Dylan Perry. So thank you all for your time, and I will yield the rest of my time. Thank you.
We got a lot of people in this room. Wonderful. Well, I'm thrilled to have the opportunity to share some of the exciting results from our James Webb program on supernova remnant Cassiopeia A. First obvious question, why Cass A? Why this particular object? Well, Cass A is arguably the best supernova remnant in our galaxy to answer key unresolved questions about the explosions of massive stars. It's the youngest example, it's fairly nearby, it has a spectroscopic classification, it's a benchmark for understanding the formation and destruction of dust and molecules, and its neutron star is very important. But even more broadly, supernovae themselves affect astrophysics so much. Here I highlight some of the applicable science cases, including the fact that supernovae are so vital to the growth of something happening.
Just making sure that your slides are being shown on Zoom. I apologize for interrupting.
Had a flow happening.
I know.
I gotta find my mark again.
Good. Terrible. I'm so sorry. Is that working, Sam? I'm screen sharing. Oh,
Well, it's very important that everybody gets a chance to see it.
And we want it
So-
recorded.
and-
So
and
that
we
is
want it
important.
recorded, yes.
We don't want, I mean, we like
Okay.
your face, but we don't want to just see your face the whole time.
Okay.
So let's see.
Did this change?
I think it was working for Natalie.
Okay.
I apologize for breaking the flow.
Okay.
This is
Well, it's happened. I have to make up for time, so I'm gonna say some jokes. So, have you heard about the new restaurant on the moon? They say the food's great, but it's got no atmosphere.
Thank you. Thank you. That's fantastic. I appreciate that. Oh, man. All right. Why? Help. We are not currently presenting. Could that be? I'm sorry,
Restart the presentation, maybe?
the presentation?
So maybe exit, go back
Let me,
in.
yeah, let me stop sharing and then I'll, oh. You well, now I just exited it, so. Hopefully this.
Is that working now?
Okay, well, that's okay. There's a
No,
delay.
no, no, no.
We'll get
People
there.
in the room gotta see it.
Of course, people
Okay.
gotta see it. We're gonna get there.
Okay.
Are we gonna get there? Hey, Sam, do you know why we don't have the slides in the room anymore?
Yeah.
It's just
We
slow.
do.
Right.
Okay, all right.
Sorry about that.
All right, that's fine. Let's, now
You want to start over?
it wants to transition. It's. Sorry, it's not, yeah, let's see this. Okay, all right,
Is it?
we can do this again. Okay,
All right.
all right, I don't need to start again, or it's recording for everybody at home. Okay, so, hey, it's great to be here. Sorry for the delay. Let's go with this again. I was just getting at why Cas A. All right, I was listing off a number of reasons. It's arguably the best galactic supernova remnant to investigate key unresolved questions of massive star explosions. It's the youngest example. It's nearby. It has a spectroscopic classification. It's a benchmark system for understanding the formation, destruction of dust and molecules, and has an important neutron star. But beyond that, more broadly, supernovae themselves affect so much of astrophysics, including the fact that they are drivers of galaxy evolution. And if we're going to have any confidence in understanding observations of the distant universe, we must have robust measurements of resolved nearby systems. And this is what Cas A provides. So it was kind of a no-brainer that Cas A was included in Cycle 1 observations of the James Webb. And in my very limited time, I can't go over everything. I'm going to highlight point 1 here, the Webb's ability to map unshocked ejecta. But throughout the talk, I'll highlight other papers that go into the other scientific goals of the original proposal. Here's the paper. It was wonderful to see it on the archive last night. 47 co-authors, 31 institutions, approximately 7 years of effort as far as planning and all the analysis. It's been submitted to the Astrophysical Journal Letters and in its advanced stages of refereeing. Let's dive into the images. Okay, so here is a composite image made from our MIRI mosaics. Standing out most is the bright kind of circular emission associated with stellar debris, or what we call ejecta, that has been reverse shocked. Surrounding it in this red and orange is gas that was released by the star prior to explosion that has been run over by the original blast wave of the supernova. The color indicates that the emission is dominated by dust. And then there in the center, smack dab, is what we've been calling the green monster, this wall of emission. It really took us, it was unexpected. It was the first thing I saw when I looked at these James Webb data, and it has been a source of curiosity for a long time. Switching now to near-cam images, we see clear differences. This reflects the fact that different wavelengths are sensitive to different physical processes. We see the main shell again, but surrounding it and projected inside is this smoky white emission that's associated with synchrotron radiation. And then hanging out in the corner is this unusual large light echo. And if I have time, I'm going to go into that afterwards. Okay. Here's figure 3 from our paper. It serves as a kind of storyboard for the many discoveries of the survey. I'm going to jump right into the most obvious question. What is the green monster? It has this fascinating structure of filaments and sheets, and it has these remarkably round holes inside of it. When we first encountered it, we thought it was associated with gas that had not been shocked yet, but we now have a different interpretation. So that came in part due to correlation with emissions seen in the X-ray thanks to Chandra X-ray Observatory. Here I'm showing a beautiful composite image that's been released as a part of a celebration of Chandra's 25 years of service. It combines Chandra, Webb, HST, and Spitzer. The correspondence is not one-to-one, but where there is overlap, it's very telling. And in work provided by Yakovink, he's able to do analysis of the spectroscopic X-ray properties that seem to most closely match those of circumstellar material seen elsewhere in the remnant. This is also reinforced by work led by Ilse de Lutz, who used data that included spectroscopic observations from our own survey, again coming to the same conclusion that seems as though the green monster is dense circumstellar material between the center of the explosion and us that has been excited by the reverse shock. Okay? Future investigations can look into this in more detail, in particular what this may tell us about what the star was doing before it exploded, and look more deeply into the nature of these round holes. Okay, now back to the one of the key aspects of this survey was to try and uncover unshocked ejecta. And so how do you do that when, for instance, you have the green monster that's essentially photobombed our image, right? It's standing in front of us and the gas inside, okay? Well, what I'm showing you here is the longest wavelength image that we have from Webb, and leveraging the multiple filters that we have and being guided by spectroscopy, we were able to actually remove the green monster very carefully, okay? Here I'm showing an inverse of what I showed you before. So black becomes white. And here is the treasure map that we wanted. Okay? It's the first time that we've ever been able to see the insides of a supernova explosion so well preserved and with such detail. You can see a kind of web-like network of unshocked oxygen-rich ejecta. And the real magic happens when we combine this unshocked ejecta map with other wavelengths. Here I'm showing a comparison to Chandra and New Star observations that show where the heavy radioactive material was distributed in the explosion. And combining all this together will provide our best tests to date for simulations attempting to understand the very complex physical processes associated with the collapse of a massive star. And then finally, just a couple words about that rogue light echo. You know, we've had decades of information from the Spitzer telescope that let us know already that the light of the supernova continues to go in all directions and heat and reflect off of interstellar gas and dust. But the proximity of this light echo, its size, and its overall morphology was truly baffling. Here I'm showing an enlargement. Okay, this is not what we thought interstellar gas looked like. You know, is the dust that is highlighted in this image not mixed well with the gas, or is the gas also structured this way? Are magnetic fields involved somehow? Is this the structure of a typical ISM clouds? These are all questions that future observations and analyses can undertake. Okay, with that, I will flash some of the highlights of what I've discussed already, and I'll just emphasize again that what I've touched on here is just scratching the surface of the possibilities, and we anticipate many more research discoveries to be made in this survey in years to come. Thank you.
Do we still see the presentation on Zoom? It's delayed. Okay, let's check it before we get started this time. Wonderful, thank you.
Okay. Hello, everyone. I'm Koda from Stony Brook University, and I want to give this presentation with Amanda Lee, who is a graduate student at UMass Amherst. And one of our other collaborators are in the audience, David Pilka. If you have any questions, please ask us. And sorry. And this is about star formation, especially the environment for star formation the parental site of star formation at the outskirts of galaxies. And as a background, I want to start from a new normal pathways to star formation. If we look at star forming region around our own sun, within our own Milky Way galaxy, or in any other nearby galaxies, most of the star formations are concentrated in the inner part of the galaxy. And this image is an example, the nearby galaxy Messier 83, M83, and red dots are star forming regions. And most of them are in the inner part of the galaxy. And the process that leads to the star formation look like this. So at the first stage, we start from diffuse, very extended atomic gas, and that starts to shrink or collapse, become denser and denser, and at some point it becomes molecular and forms an object called molecular cloud. And molecular clouds typically have very dense core at the centers, which we call hearts of molecular clouds, which are surrounded by less dense molecular gas, and this whole thing is called molecular clouds. And star formations are actually happening in these hearts of molecular clouds, the dense cores of molecular clouds. That's a normal star formation. And we didn't expect to find star formation at the outskirts of galaxies, but about 18 years ago, surprisingly, the NASA's Galactic satellite found a lot of young stars, newborn stars, at the outskirts of these galaxies by David Stilker, one of our collaborators. So astronomers became interested in the environment for these star formation and looked for the molecular clouds, the parental site of star formation, but couldn't find any until now. So we looked at this tiny region in M83, and this observation is already very difficult, very expensive in terms of telescope time. So we couldn't observe the entire galaxy. We needed to focus on a small region. But within this small region, we found 23 molecular clouds, the parental site of these star formation, for the first time. And we also found that these molecular clouds are unusual. So what we see are just the hearts of molecular clouds, and the envelope of the clouds are invisible. So we see only the central part of the clouds, and that's why we can see only the central part of a molecular cloud, and that's why it was very difficult to find them until now.
Can you hear me?
Yep.
Okay. So the discovery of the hearts of the molecular clouds with ALMA now allows us to link the last two stages of the star formation process, since now we have found the formation sites of these young stars in the galaxy outskirts. But since there is molecular gas, we also expect there should be atomic gas from the first stage of the star formation. And so within the same region, we looked for that atomic gas, and we found there's actually a lot of atomic gas, surprisingly, compared to the amount of molecular gas that we found. And so by solving the first mystery, which is the mystery of the formation sites, now we have another mystery, since we don't yet understand why this atomic gas has not converted to molecular gas efficiently in this environment. And so this research meant a lot of data from different telescopes around the world. So for the diffuse atomic gas, we used the VLA and GBT. In order to actually discover these hearts of the molecular clouds, we used ALMA. And to characterize the young star forming regions, we used Galactic and Supernova. This study involved a lot of astronomers around the world, and each of the local contacts within each country is shown in blue. But everyone who is involved and from the United States is here at the conference. And so in summary, we knew that there were a lot of young stars forming in the outskirts of galaxies, but for many years, researchers weren't able to actually find their formation sites. Until now, since for the first time with ALMA, we have actually discovered the formation sites. So we have one mystery solved, but now we have another mystery, since within that same region, there's a lot of atomic gas, and we don't understand why that atomic gas is not converting to molecular gas efficiently in this star formation environment. Thank you, that's it.
Great, thank you very much. So I get to spend a couple minutes here talking to you guys about a new galaxy that was discovered called J0613 plus 52. It's a very exciting and original name for it. So this is an object that, sorry, this is a little slow to respond. So this is an object that was actually discovered as part of a survey of neutral hydrogen at galaxies. This was a survey of low surface brightness galaxies. These are objects that are about 1 magnitude or more fainter than the night sky, so fairly difficult to see. And it was a multi-telescope survey, so using a variety of telescopes around the world for these observations. And understandably, we use these telescopes often to go look at the same object to make sure that we were calibrating things correctly and detected the same thing. And in the process, we found a slight anomaly, which was we found a real discrepancy between some results from the Green Bank telescope and the Nancy radio telescope for one particular object. And upon looking a little bit closer at it and spending far too much time, we discovered that we had actually mistyped the coordinates in the GBT catalog. So we went back and said, all right, well, what did we detect? You know, this is something, unfortunately, astronomers do occasionally late at night. And so we went back and looked, and what we actually found was there was nothing there. There was no known galaxy within 112 megaparsecs of what we had seen. So if you go and you want to actually see what the sky looks like there, this is a 3-color image from the digitized Sloan Sky Survey, looking at that part of the sky. And then sitting on top of this are now the GBT beams. And so these are the 9.8 arc-minute GBT beams on the sky. White means we didn't detect anything. The colors show you where we made a detection and then the offset of the central velocity of that detection to the center detection. And then the thickness of these rings actually show you the intensity of the neutral hydrogen that we detected in this area. So if you want to look at this slightly differently, you can take just the blue beam here, the darkest blue beam, where we detected the majority of the neutral hydrogen intensity. So this is possibly where the whole galaxy is contained. We're not sure yet. And you can look at the actual numbers. And so the top line here shows you the values that we found for the distance to the galaxy, the total gas, as well as the rotational velocity of the galaxy, which is essentially equivalent to the dynamical mass of the galaxy. And what you can see here then are the numbers show you a fairly normal spiral galaxy. Really, you've got something that is probably fairly organized. It's rotating at a nice speed. It's got a decent amount of neutral hydrogen gas, so about 2 times 10 to the 9. That's pretty good. The second line shows you our ability so far to measure the central surface brightness and the luminosity of this galaxy. It's not great. This is not a particular popular area of the sky, unfortunately, for existing surveys. And so we are able to push it at least to below 25 magnitudes per square arc second. So we know that much. So what does this really mean? It's just a bunch of numbers. So let's take this again and take a look at where this sits on the sky when you compare this object with similar objects. So now I'm not looking at normal spiral galaxies. Those would actually sit below this plot and kind of cover more or less the whole x-axis there. But I'm comparing it against similar galaxies. So in green are the H1 rich, fairly dark galaxies found by the Alfalfa survey. And then the blue are a number of other objects that have also been found recently that are considered dark or almost dark galaxies. And then labeled are the 2 galaxies most closely comparable to this one. So you can see there are definitely objects that are lower surface brightness out there. We know that. I haven't been able to push the surface brightness on this yet. But what's really sticks out about this galaxy is the fact that it is essentially a normal spiral in terms of its gas mass and in terms, most importantly, of its dynamical mass, of the rotation speed that we see with this. So it really sticks out in that area. So with that, the obvious question is, what is it? Well, I already told you it's pretty low surface brightness, potentially dark. It's very isolated and undisturbed. But again, it's got the size of a normal galaxy. So you put those things together and ask the obvious question, well, what the heck is this thing? And why is it fairly uninvolved? And the answer, I believe, is pretty simple. So we have an object, a galaxy-sized object, that's very, very diffuse. And in fact, the gas is too diffuse for ready star formation within the object. But it's got something else that makes it very different than most galaxies, and that is it's also very isolated. So that means it doesn't have any interactions nearby to spur star formation or potentially tear it apart and start the star formation that way. So that means what we might have here, is the discovery of kind of a primordial galaxy, a galaxy that's so diffuse it hasn't been able to form stars readily, but it's also isolated enough that nothing has come along to trigger that. So with that, you have to ask the question then, is this thing unique? Well, the answer is it's clearly uncommon. If it wasn't uncommon, we would have seen this with some of the great surveys that have already been done. Arecibo had a lot of good surveys with its Alfalfa instrument. And of course, we also have HiPass, and they have never found anything quite like this. So it must be rare. Doesn't mean it's unique though. And what we really need to do to follow this up is to get a full sky survey outside of just the swaths that Arecibo was able to do. With a telescope like the GBT, there's a new instrument being built called Alpaca. The brand new logo's on here. Alpaca is actually going to be able to survey the sky to incredibly deep areas, comparable or deeper than what Arecibo could do. So it might be able to find these objects with us for this. So quick summary on this. We have a low surface brightness galaxy. It's not a dwarf. It's a fairly large galaxy. At the very, very low surface brightness, we've been able to find for an object like this, not having a central bulge. And it's probably its isolation that's the cause of its low star formation, making it potentially a fairly primordial galaxy. Thank you.
Give it a minute to show up in the room. Oh, you're good.
Okay, last but not least, I'm going to talk about something completely different. The origin of odd radio circles. So I'm Alison Coil from UC San Diego. In 2021, a brand new class of extragalactic objects was discovered. That doesn't happen very often. These are called ORCs, for odd radio circles. They're very large rings of low surface brightness radio continuum emission on the sky. They're 1 arc minute across. Just for context, that's really, really big. There aren't things that size on the sky. These were discovered by the Australian SKA Pathfinder, a new radio telescope that's sensitive to faint emission. The first few objects are shown on the right there. That's the discovery paper by Ray Norris. So you can see these large rings of radio emission. Many have galaxies at the centers in their imaging, and the imaging gives them photometric redshifts of around 1/2. That means that they're extragalactic and they're at very large distances. That implies diameters of those radio rings of hundreds of kiloparsecs. That's way bigger than galaxies. There aren't really things that scale in the universe. So the origin is completely unclear. The ORC on the bottom is the one that I'm going to show you new data on. So we went to Keck and used the Keck Cosmic Web Imager to look at the host galaxy of ORC4. On the left, that's showing you the galaxy spectrum. I know that looks boring to you, but I thought that was amazing. There's this really strong line. That's oxygen 2, singly ionized oxygen emission at a redshift of 0.45. We can see a few other lines. On the right, that's a map of the oxygen 2 emission, and it's pretty round. We also have information on the kinematics or velocities of that ionized gas, and we find that it has a high velocity dispersion, which means that the gas is being churned. We also, from that spectroscopic redshift, we know the distance. It's definitely extragalactic. That implies that the ORC ring, the ring of radio emission, has a radius of 200 kiloparsecs. A kiloparsec is 3,300 light years. So these are huge radio rings. The host galaxy is massive, very massive, and the stars are old, and it's not forming stars anymore. So if we allow for a burst in the star formation history of that host galaxy, the best fit of the data on the left, which is the imaging at different wavelengths, shows that there was a strong burst of star formation about 1 billion years ago. And since then, the galaxy has not been forming stars. This is the most technical plot I'll show. This is showing the oxygen 2 gas emission. So this is the amount of the oxygen 2 gas relative to the emission from the stars as a function of the distance from the center of the galaxy. And the black line there is showing the oxygen 2 in this ORC host galaxy. And on the lower left down in the corner is the data for comparable massive galaxies that aren't forming stars anymore. So what you can see is that this galaxy is really unusual in terms of the amount of oxygen 2. There's 10 times more oxygen 2 at any given radius. And also it extends 10 times larger than oxygen 2 in similar types of galaxies. So basically massive galaxies that aren't forming stars anymore don't have much oxygen 2. And when they do, it's just in the center. This galaxy has loads of oxygen 2 really far out. So what is causing that? We also have Gemini GMOS long slit data that goes to longer wavelengths. We can use the line ratios. We see other emission lines that points to shocks. So we think that that is shocked gas. Shock is a heated, compressed gas. Okay, so here's what we think is happening. So here's a computer simulation run by my collaborator, Cassie Locust. She ran a suite of simulations trying to model what we were seeing, both in terms of the large scale radio ring and also this enormous amount of shocked gas in the host galaxy. I'll be honest with you, when I saw this amount of oxygen too, I thought, I don't know what this is. It's time to call in a theorist. So I went to the theorist, Cassiopeia, who had been working on these simulations and models of outflowing galactic winds. So when a galaxy has a burst of star formation, there's also a lot of the really massive stars don't live very long and they die at the same time. When a star dies and creates a supernova remnant, as you saw, it ejects gas out into the surrounding medium. If you get a bunch of supernovae going off near each other, it can eject the gas all the way out of the galaxy. That's called an outflowing galactic wind. So in this model in the lower left, there's a galaxy. It's blowing a really extreme outflowing galactic wind. It's pushing the gas out into the surrounding medium. This is showing 3 different times since the wind started, since we think there was a starburst. So there's a forward shock and a reverse shock while this wind is happening. When the wind shuts off, that's the center panel, the forward shock continues to large scales, and then the gas that's basically been swept up by the shock falls back onto the galaxy in this reverse shock, and you get gas raining back down onto the galaxy, and you get this turbulent medium. So eventually on the right, that's when we think we're observing this source. You have this large scale radio ring of synchrotron emission, and then on smaller scales, all of this oxygen 2 shocked gas in the host galaxy caused by the same energetic event. So if this works, I'll show. So here's a video of the density. So the wind was happening there, then the wind shuts off. When the wind shuts off, these 2 shocks decouple. One moves to large scales, one moves to smaller scales. So the same event caused both the large scale Oort radio ring and the smaller scale oxygen 2 shocked gas emission in the host galaxy. So we think a starburst driven wind drives this forward shock out of the galaxy. When the wind shuts off, the shocked wind gas from the reverse shock travels back towards the galaxy as the forward shock continues to larger scales. So one of the theories for the origin of ORCs is a shock from a starburst driven wind. We observed extended oxygen 2 over an extent of 40 kiloparsecs in the Oort host galaxy, basically throughout the whole galaxy. That's consistent with it being shocked wind from the same energetic event that caused the Oort in the first place, as some of the gas falls back onto the host galaxy. So this motivates the origin of ORCs, or at least this ORC, as an outflowing galactic wind. So it helps solve the mystery of what causes these large rings of radio emission. It also helps us see these outflowing winds after they've shut off. These are transient events. You have to catch them in the act. Here we can see it after it's ended. Also, this allows us to probe the properties of gas very far away from galaxies, hundreds of kiloparsecs away, where there is gas out there, but it's very low density, it's very hard to detect. And so this is a way to constrain the properties and physics of that gas on really large scales. And I should have mentioned the picture in the upper right there is follow-up Meerkat data on the first ORC with higher resolution, where you see that sort of glowing orb. And at the very center there is a central host galaxy. Thank you.
Wonderful. Thank you so much to all of our presenters. We're going to go ahead and move into Q&A now. Do we have a mic runner? Okay. So Ben is going to take the mic around. Go ahead and raise your hand, and remember to identify yourself and your affiliation and who your question is for when you ask the question. Let's start with Camille here.
Camille Carla, Skying Telescope Magazine. I have 2 questions for Dan. First, could you please elaborate on what you're learning from seeing the interior of the explosion? And 2, what is your current hypothesis for what those weird bubbles are in the green monster?
Great. I can't see you. I just hear a voice. There. Okay, right in front. Great. Thank you. All right. How much time do we got? I could go into great details. Look, we're trying to understand the type of star that was there beforehand and how the explosion proceeded. Okay? And one of the best ways to investigate that is to look at the gas that's closest to where the explosion happened. And that's what this unshocked ejectomac provides to us. Okay? Previous to this, we had ideas from Chandra that shows where the iron is today, which would have traced where the nickel was released, and then New Star provided a titanium-44 map. We had hints that this shaped the interior through prior work that myself and others had done, but this web observation provides a kind of clarity that we never dreamed of before, being able to see how the explosion dynamics, including the radioactive heating of that material and neutrino-driven heating has shaped the interior. Okay? So long answer short, having this map is close, it shows where the gas closest to the original explosion took place. And it's not perturbed or disturbed by the reverse shock but that is eventually going to move its way inward. And you asked a second question.
And to clarify, the gas, this is the gas that was thrown off in the explosion.
Yes.
Okay.
Yes.
What are the holes in the green monk?
Oh, right, great. So a lot of mystery behind that, but our best understanding is that the holes were introduced by very tiny ejectonauts. So try to imagine shotgun spray. Okay? And we have a kind of a sheet of circumstellar gas that's left by the star beforehand. And then all of a sudden you have these very tiny ejectonauts. And we've seen this prior in HST observations, hundreds of AU in size, very, 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 very small. And these pierce through the clouds and drive these expanding tangential shocks that form. There's very few mechanisms in the universe that can make such round objects. And this is the one that seems to be the best explanation.
Okay. Thank you.
Hi, thank you. This is Clara Moskowitz with Scientific American for Dr. O'Neill. If you have found a nearby primordial galaxy, why is that exciting and what might we be able to learn from that?
Sure. So what's really exciting about it is the concept of low surface brightness galaxies or ultra diffuse galaxies, pick your favorite nomenclature, has been around since the late 1970s, early 1980s. And they've always been a class of objects that pushes the star formation and galaxy evolution theories to the extreme. So you come up with a great theory, a great simulation, and then you start to wonder, well, can this hit the extremes? Can it hit those little dwarf galaxies? And can you hit things like, create things like Malin 1? And when you start to look at objects, ultra diffuse and low surface brightness galaxies, a lot of times the answer is yes, you can create them through interactions, through watching objects get ripped apart and either removing some of their stars or otherwise changing their formation scenario than they would be in isolation. So this might be our first chance to really take a look at what happens to star formation in a diffuse environment where nothing has come along to tweak it. There's been nothing either, like you get at the edge of galaxies, you might have supernova and so forth, but you really got just a very quiescent situation where you can really go in and start to look at your star formation theories to understand what happens in these very diffuse environments and then come back and reapply them to galaxies like our own Milky Way. So it's really just a potentially beautiful test case for us to be able to look at things. Thank you.
Thank you.
Let's come up here to Martin.
Thank you, Martin Ratcliffe, Evans and Sutherland, for Dr. Butterfield. In undergrad, my magnetic fields was my worst topic. So this question might be naive. How do you unravel the magnetic field of that clump from a magnetic field embedded in the supernova remnant that's expanding out because it seems to be spherically symmetric with that, and the ambient magnetic field in the galaxy?
Yes.
So it is something that we have to take into account is when you're looking at dust polarization observations, you are accumulating your magnetic field along your line of sight. However, when we look at a comparison of what the Sophia observations look like, and we actually image the source itself, most of the emission is coming from the ring. And so it's more weighted towards those features that are associated with the ring for the magnetic fields that we're measuring in there. But that is something that we have to take into account, especially towards the lower intensity regions, like towards the center, and then towards the exterior of the ring where the intensity starts to go down. Then we start to run into those effects of potentially additional magnetic fields along our line of sight towards the center of the galaxy, just because we are looking through so much material between us and the center of the galaxy. But yeah, for the ring itself, since most of the emission in the Sophia observations are associated with the ring, we're suggesting that a lot of the magnetic fields, or most of the magnetic fields that we're measuring in that region, are associated with the ring itself, and it's localized.
Let's take one from online, Carrie. Over here.
I have a question here from Bill Waller of the Galactic Inquirer for Alison. What available line ratios indicate extensive shocking?
Yeah, so this is not part of the paper that we just published. We have another paper that we just submitted with the Gemini GMOS long slit data. So there's not spatial information, but with that, we were able to cover the full optical spectrum. And there you can use line ratios like N2 to H alpha, O3 to O2. And there's multiple diagnostic plots where you can distinguish line ratios from star formation, AGN activity, or shocks. So technically, these line ratios are what we call liner-like, which could be an AGN or could be shocks. But we already know that this galaxy, while it does have an AGN, which is an accreting supermassive black hole at the center, it's not very bright in optical light. The optical SED had only a 3% AGN fraction contribution. So we really don't think it's an AGN. So we think that it is shocks. With Keck KCRM, which is the red arm of KCWI. So the observations I showed were just this blue optical integral field spectrograph. This summer, we're going to go back. They have a brand new red arm that will allow us to get the redder wavelengths, and then we'll be able to make two-dimensional spatially resolved maps of those line ratios and make sure that those shock line ratios really do exist all the way out throughout the whole galaxy. And then that will confirm that it's definitely not from an AGN, it's from shocks.
Robert Schilling, freelance from the Netherlands, with a couple of basic questions for Alison. How many of these OCRs do we know? How rare and how long-lived are they? And what could be the cause of this starburst event?
Okay, great multiple questions. So orcs are newly discovered. There's around 11 known right now. That includes some candidates. It's not entirely clear when you call it an orc and when it's a candidate, but basically there's 11 candidates or known orcs. Of those, one definitely seems to be an intergalactic supernova remnant near the Large Magellanic Cloud. That one's kind of an oddball one. There's also one that looks like it's an AGN that's also kind of an oddball one. The rest of them look a lot like the one I showed. They're extragalactic. They have a red galaxy at their center. In terms of how common they are, right now there's not that many known, but they just started doing these large radio surveys. They're not that common, but when you observe more and more of the sky, you discover more of them. So basically every sort of 2 to 3 months these days, there's a new paper saying, oh, here's a new orc. So they're going to be a lot more discovered as these multiple radio arrays come online and continue to do large surveys. In terms of what caused the starburst, good question. These are really massive galaxies. We know even for the other ones that I didn't show you that the SEDs look like they're massive red galaxies that aren't forming stars anymore. Galaxies that massive, to get that big of a starburst, you probably need a major merger event. So two galaxies that are massive collide. When they collide, it compresses a lot of gas. You get this strong burst of star formation that creates the outflowing galactic wind. That's my guess.
Right here. And then to Leslie afterwards.
Hi, I'm Danya. I'm an undergrad at the University of Connecticut, and I have a question for Alison. So you were talking about when the wind stops, that there's like two shells, so one keeps expanding, and I was wondering for the one that retracts, like what is the force that causes it to retract?
Yeah, so the question is basically, why is there this reverse shock? So this came up in an earlier talk. These talks are a little more related than they seemed initially with the expanding shells and the reverse shocks. So this is a generic feature of an outflow, not just a wind. A supernova remnant has this. So basically something happens, you expel a lot of gas, and as that gas decelerates, so that gas is going to hit the ambient medium. It's going to slow down. As it decelerates, that deceleration is what causes the reverse shock. It's only a reverse shock in the reference frame of the expanding shell. It's just going slower than the other one. And they're going basically together as long as they're still being pushed. It's when that something, whatever is pushing them, supernova or whatever, stops, that the outward one just keeps going. But the forward one, you've basically evacuated all of this gas. There's this underpressurized region. And where's that gas going to go? It's going to go back to the low pressure. So it just falls back to where it came from. Does that explain your?
Yep, thank you.
Okay.
Leslie Sage, Nature. So this is for Amanda and Jim. You referred to the origin of the atomic gas as mystery. that implies you've been able to exclude cold flow accretion. And how have you been able to do that?
So what we said is the conversion from the existing atomic gas to molecular cloud is a mystery. It looks very inefficient in this environment. There are a lot of atomic hydrogen, but there's not much molecular gas. And we still need to understand how that conversion gets triggered in this environment. Does it answer to your question?
Not really. Cold flow accretion, we know what happens. And it can take a long time for the gas to cool sufficiently to produce molecular clouds. So why is it not just another example of cold flow?
Okay, so thanks for that question. Yeah, the cold flow could bring the gas there. But converting that gas in, the atomic gas into molecular clouds is the process we are, talking about. And we still don't understand what really triggers that conversion locally to bring more atomic gas into molecular clouds. So large scale, yes, there is a gas flow from larger environment, but locally, we don't know how that atomic gas is converted to molecular clouds.
Good, Ethan.
Thank you. This is Ethan Siegel from Starts With a Bang. This question is for Karen O'Neill. I'd like to ask you a little bit more details about this possible first primordial dark galaxy. You mentioned that there have been no objects found like this with Arecibo across a variety of surveys, and I'm curious how much of the sky those surveys actually took up to look for this class of objects that didn't resolve anything. And I also, well, I'll let you answer that one first, and then I'll ask the next question for you.
Sure. So the Arecibo sky goes went from a little bit below 0 degrees declination up to almost 30 degrees declination. I would have to review all the various alfalfa and alds and all the different surveys, but you can presume that they covered a lot of that area. Now Arecibo does have a little bit more of an issue with a little bit more of an issue with radio frequency interference than the GBT does. So if you're talking about distance wise, the GBT covers a bigger area. The GBT can cover all the way, the majority of the sky. It covers 90% of the sky, so we have a much bigger swath to look at. So that's a partial answer to your question. It's not really a very good answer to your question, because the reality is it is surprising that Arecibo has not found this. The alfalfa survey in particular was quite extensive, and the sensitivity of the alfalfa survey was similar to the sensitivity that we had that caused our detection. So yeah, we got a little bit lucky. There's no other way to put it than that. But the fact is the GBT can cover a bigger area of the sky. So we clearly have an object that is rare. There can't be a lot of them out there. Alfalfa, ALDS, and the other Arecibo survey, whose acronym I just forgot, should have found them if they were common. Right. But we kind of know that. If you look at the universe, you know that there's a lot of galaxies out there. You look at galaxy formation and evolution theories. There's a reason we talk about galaxy interactions. It's because that's where galaxies are. And the more we've delved into objects, the more we found that they commonly have neighbors near them. So to find something that is so isolated is very unusual. I'm not willing to say unique until somebody has scanned the entire sky to that sensitivity, but it's clearly very unusual to find this. And I think most extragalactic astronomers would agree that you're just not going to find a lot of objects sitting off by themselves very commonly that are fully galaxy sized. And that's part of what makes this different. But I truly do believe that if we can push the sensitivity of our existing telescopes, we don't have Arecibo anymore, but we do have the GBT. FAST is online and certainly doing fantastic science as well. So just like all instrumentation, I think as we start to push the sensitivity, we're going to see more unusual objects and possibly a few more of these, but how many, I don't know.
Great. So assuming that, this one is real and it's, what you think it is, are there now other wavelengths of light you can look in to say, oh, we've looked at this region of sky with something better than the DSS-2? And do we see spectroscopy? Do we see absorption features? Do we see, can we figure out what elements are in there? Are there magnetic fields? Are there stars? Is there any data like that exists? And if not, does someone plan on getting it?
Sure. So that's a great question. So the reality of it is that let me first say that so let me just go to low surface brightness galaxies, stuff that have a surface brightness around 23. These things have been around forever. I did my dissertation on them far longer ago than I want to think about. And it takes a heck of a lot of telescope time to look at these. And unfortunately, so if you just look at low surface brightness objects, so these again will give us spiral galaxy sized objects that are similar, although we have light for them. It can take 100 or more hours of VLA time at the biggest array configuration, say D array, to just be able to detect these things and see them. CO gas has only been found in these objects. There's been a few people looking at this. CO gas has only been found in these objects in the dense cores, never out in their diffuse arms. And that's again taken many tens of hours on the largest telescopes that are out there. So this is a difficult game to play. Having said that, of course, it's a game we're going to keep playing. Of course, we're going to go out and go get more optical images of these to see if we can push this down and finally find this. There has to be stars there. It's not like there's going to be truly dark, but a dark galaxy means that our current instrumentation can't see them. And that's really what we're going to push. And so we need to go out there. We should be able to get images out to a few magnitudes fainter to see if we can see anything out there. It's a tricky game. You got to get a big telescope to collect it. And then you do a horrible thing and you actually sum all those pixels together instead of using the pretty image you have to see if you can get the light. But yeah, that is absolutely the next step. I will say, though, that this is real. We have spent many tens of GBT hours to track this down. We've confirmed it through multiple observations of different instrumentation on the GBT. So we know the gas is there. We know that part's real. And it's really just a question of going to the other wavelengths and convincing the tax that they should spend the many hundreds of hours on this object instead of going and looking at other objects. So it's a tough game and it's going to take a while to really push this through because of that.
All right, unfortunately, that is all of the time we have. So we're going to go ahead and wrap this up, but I'd like to be able to continue the conversation if any of you have further questions. So hopefully if the speakers don't have somewhere to be immediately, you're welcome to come up and talk to them. Otherwise, please feel free to leave. And also, just a reminder to everyone that we do have a Slack channel. So you're all welcome to join that. You're all welcome to join that. And maybe you can continue conversations there. It's #press-conferences. So feel free to hop on that. So I just want another hand of applause for our speakers. Thank you so much. That was really great. Thank you so much. And thanks to your press officers for helping you prepare for this and getting the press releases together. Thanks to our sponsor, USRA, for making the press office happen. And we hope to see all of you back this afternoon for stars, protostars, and more clouds at 2:15. Thank you so much for being here.